Reading Physical Systems and Signals class. This is the video that I promised you about basic systems and some work examples. One thing, let me begin by saying that if you downloaded set 4 of the notes before 1:30 on Wednesday, you might need to do it again because the original version of those notes that I uploaded got corrupted in the upload process and resulted in the PDF only having a single page in it. The version up there now works. What I'm going to do is I'm going to take you through the notes. And as I said in the announcement on Blackboard, you can just work your way through the notes. Everything's in there. And in fact, there'll be things in the notes that I won't go through, so you will have to read the notes either way. But if you want some pointers, I am going to go through them. So I'll begin by sharing my screen. And here we go. You should be able to see a set of notes and starts out with some pictures of waves. And what this set of notes is all about is systems and classifications of systems. So I begin with defining what a system is. It's basically a mathematical model, and I show you some mathematical notation for it. And basically, what it is it's an operation that gives us a rule for transforming inputs X into outputs Y, and pictorially it can be viewed in a number of ways, which I show you on this slide. Then we can look into a variety of sorts of systems. So if we look at a continuous time system and a discrete time system, we could just look at different sorts of outputs. One, the continuous data, or two, the sequences of data. And again, those are the pictorial representations. Then what I'm going to do is look at some examples of systems. A good example is a simple RC circuit that you saw in electronics and that we've already talked about here in the class before. The basic idea is that we can develop a way of looking at all sorts of different situations that are described by the same mathematics. That's called a system. And the system can then all be analyzed in the same way, and we'll actually develop ways of analyzing systems that are different to some of the ones you've seen before. But looking at two examples, we could look at a circuit, and there I've given you the source voltage and the capacitor voltage. The source voltage is the input, the capacitor voltage is the output, and you can derive a relationship that relates input to output, basically making use of Ohm's law, eliminating the voltage across the resistor because that's neither input nor output. We can come up with a relationship which I went through in class, and you see we arrive at a first order differential equation that relates output to input. We could also consider the motion of a vehicle, and that's the second example. And here we have an applied force that we've called F, and a retarding force, which is simply proportional to the vehicle velocity V, where rho is just the proportionality constant. I think when I did this in class, I had a stray m in there. This version of the derivation is correct if you see a stray m at some point in your notes. The point is, when you work the details through, it comes out to an ordinary differential equation, which is again first order, and which fits into the same form, which is that it's the derivative of the time derivative of the output plus some constant multiplied by the output is equal to some constant times the input. So systems enable us to solve a variety of examples. And again, I've included the bank balance problem, which we also talked about in class. Now what I want to do is go on to some new things, and we'll talk about the various sorts of systems. And looking at this, I somehow managed to leave a T out of without, but it's systems with and without memory. So a system is called memoryless if its output for each value of the independent variable at a given time depends only on the input at that time. I just give you an example. I mentioned that a resistor is also an example. Then I introduce what we call the identity system, which is a system whose output always equals its input. Now, you might wonder about the importance of identity systems. Let me alert you that they're quite important. An example would be what is called a zero gain amplifier. Sometimes we put a zero gain amplifier between two systems. Why do we do that? Well, the reason that we do that is it acts as a buffer between the one piece of the system and the other piece, and it means that basically we can get a signal out without that signal affecting the system that it's coming from. We'll see identity systems more than you might have imagined. Another sort of system is an accumulator or a summer, and not summer in season in terms of a season, but a summer in terms of something that performs sums. And so you can see that here's an example of a discrete time system with an accumulator. We could also write a delay equation, and a capacitor is a pretty good example of a system where we have a system with memory. So anyway, memory means really that the system stores energy, or very often that's what it means. But roughly, systems with memory retain or store information about input values at times other than the current time. Then I go on and I look at invertibility and inverse systems, and basically you can see that I've diagrammed both a continuous time and a discrete time example, and with the discrete time coming up later. But this is the continuous time example where we have an input and it is recovered. I've diagrammed a discrete time system, but I didn't actually give an example. So an example, though, of a non-invertible system is one that whatever you put into it, nothing goes out of it. A former student who I knew who couldn't do his electronics exam on logic gates spent the exam period writing what he called the anything gate, which he designed a gate where whatever you put into it, nothing came out. I gave him some points for creativity, even though he couldn't answer the question. But anyway, another example is where we look at the quadratic function of the input, because the input could either be a negative or positive here, and we would get the same output. And so that means that this system isn't invertible. Next, we look at causality, so basically a system is causal if its output only depends on input from the past and the present. We also call such systems non-anticipative because they don't anticipate future values. An RC circuit is causal, for instance, and I diagram at the bottom of the page an example of something or some things that aren't causal because they use values from the future. All memoryless systems are also causal. And let me say, as I've actually already told you a couple of days ago, causality is not essential, because sometimes we'll be looking at systems where the independent variable isn't time, and then non-causal systems make sense. I show you a test for causality, and in the example that I work, I pick one that might have looked like it would pass to you, but it actually fails. I then go on to look at stability, and basically stable systems are where we have small inputs and the responses that result don't diverge. Formally, then, if a stable system is bounded, that means its magnitude does not grow without bound. Then the output is bounded. So what I do then is work an example about whether a couple of systems S1 and S2 are stable or not, and you can see the details. And I work one just looking at the variables, and I work a second example just using bounds. Then I go on to illustrate time invariance, and I write the conditions for CT and DT systems to be time invariant. And I work an example to show you how to figure out if a system is time invariant. Then I introduce linearity, and linear systems are ones that obey the property of superposition, which you should have met several times before. The two properties are additivity and scaling, and scaling is sometimes called homogeneity, and this is a really useful concept. I've actually published 4 papers relating to scaling and homogeneity, which deduce general properties of systems. But anyway, then I go on to combine time invariance with linearity, and we introduce linear time invariant systems, which are the systems we'll spend much of our time looking at this semester. And so I'll then show you how to figure out if a system is linear. I work 2 examples, and we get one that is nonlinear. Make sure you understand the details. And that's basically it. So that's a brief overview of the notes on systems. Then what I do is I have some examples, and I'm going to pull those up as well. So I'll stop the share here, and then I'll quickly restart it, but I'm going to share this time a different page. And of course, I managed to actually share the wrong one. Okay, so now you should be able to see a different page. And what I do on this one is I take an RC circuit, I introduce inputs and outputs, and basically I ask, first of all, to find the input-output relationship. And then I ask, is the system memoryless, causal, linear, time invariant, and stable? And so I put in a function x of t, and I assume the capacitor is constant, and basically then I write an expression for the output, and you can see it's not memoryless. And then what I do is I go through and examine each of the conditions in turn. And so basically we have the basic properties of that system. Then what I do is I go on and look at a different sort of circuit. And this sort of circuit is a simple multiplier. It multiplies a function x by a cosine function to produce an output. And again, I ask what the properties of this particular system are, and I go through and work through all of the cases. And again, I want you to make sure that you're able to do that and to make sure that you understand the results. So that's just a quick overview of what the notes say. The notes are the definitive version. Please study them carefully. I will answer any questions that you might have next week, but I hope that everything is laid out clearly so that you don't have any questions. And with this, we'll have done all of the basic definitions of continuous time signals, most of the basic definitions of discrete time signals, and we have done all of the basics of systems. So we are now, after 3 whole weeks into the class, we're at a point where we can actually start looking at signals and systems. Up to now, we were really pulling together lots of information, some of which you will have known before, some of which you'll have seen in different form before, and some of which I know was wholly new. But all of that is what we'll be using for the rest of the semester. So we have the foundations. And if you are have a problem in some area, the likelihood is that you probably need to go back and review the basic definitions before trying to solve the problem that you're stuck on. So let me stop sharing. And I hope that Thursday and Friday are not too bad, but anyway, make sure you keep up with your work, and I will see you on class in class next Tuesday. So I'm stopping the recording at this point.